Hello friends, myself Dr. Nandakumar Raubale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 1. This is our 36th lecture. In previous lecture we have discussed numerical on steam flow through nozzle. Today also we are going to discuss one of numerical on steam flow through nozzles. But in this case we are going to deal with a problem where multiple nozzles are used for expanding the nozzle. In these multiple nozzles are used in parallel. So now let us see what is given in this problem. So a dry saturated steam with initial pressure, that is pressure P1 11 bar, is expanded to pressure 1.5 bar. Pressure P2 is 1.5 bar. So here initially dry saturated, the term dry saturated indicates the dryness fraction of steam X is equal to 1 or X1 is equal to 1. So initially the steam is dry saturated and that is expanded through the convergent divergent nozzle. Type of nozzle is convergent divergent nozzle. So initially cross-sectional area reduces and afterwards it is going to increase. So this is section 1. And this exit is section 2, and the minimum cross-sectional area is known as a throat T. Now pressure P1 is given, pressure P2 is given. Condition of steam when it enters into the nozzle is dry saturated. So if we want to show it on molar chart, HS chart, so this is dry saturation curve and this is a pressure curve P1, PT and P2. So this is curve for pressure P1, this is curve for pressure PT, throat pressure, and this is a curve for exit pressure. So initially steam is dry saturated, means 0.1 is on this curve, then it is expanded up to throat and then up to the final pressure 0.2. So now what is given here is pressure P1 is given, dryness fraction is 1, and final pressure P2 is also given 1.5 bar, and type of nozzle is convergent divergent nozzle. Then he is saying that the flow rate through the nozzle is 4 kg per second. So total gross flow rate of mass flow rate of steam is 4 kg per second. The cross-sectional area of a nozzle at throat. So here he has to give cross-sectional area of each nozzle. The term each is missing. Each nozzle at throat is 2 centimeter square. If 12% of heat drop is lost in friction, so heat this is the area at throat for one nozzle, 80 for one nozzle, and 12% heat drop is lost in friction, means nozzle efficiency is indirectly given. Nozzle efficiency 100 minus 12 is 88%. Heat loss due to friction is 12%, means nozzle efficiency is 88%. Then find the number of nozzles and exact throat area and exit area of the nozzle. So now number of nozzles have to be obtained, and throat area, so actual throat area or total throat area 80 has to be calculated, total throat area, and exit area of a nozzle, so A2 has to be calculated. So now The data given we are going to collect here in a table. So given data, steam is dry saturated means dryness fraction at point 1, x1 is equal to 1. Then pressure at the initial condition is 11 bar. Then at exit pressure is 1.5 bar. Mass flow rate of steam is 4 kg per second. This is gross mass flow rate. Gross means total. Area at throat is 2 centimeter square means it is area of each nozzle. Then heat drop is 12%, that is nothing but indirectly nozzle efficiency is 88%. Then he is asking us to find out number of nozzles. So if we know total area of all nozzles, and if we know area of each nozzle, area at throat for each nozzle, then total area divided by the area of each nozzle gives us number of nozzles. So here what is given is area of each nozzle is given. If it is possible for us to find out total area at throat, and then by dividing total area at throat by area of nozzle, area at throat of each nozzle, then we get number of nozzles. Then what is our aim? Aim is to find out total area at throat. So area at throat is given by m into specific volume Vt divided by capital Vt. Actually this is mass is equal to AT Vt divided by small vt. So here this is rearranged and we are going to get area at throat. So to find out area at throat, mass flow rate is given. So this mass flow rate of steam is gross means total mass flow rate of steam is given. So mass flow rate is given, specific volume of steam we have to calculate, and velocity of steam at throat. If we know these parameters, then we can find out total area at throat. So to find out velocity at throat, we must know enthalpy at inlet and enthalpy at throat. So if we know enthalpy at inlet and enthalpy at throat, then we can find out velocity at throat. So now here there is one assumption, there is no friction between inlet to throat. After throat the friction exists, therefore here efficiency is not multiplied. Then here Pt divided by P1 is equal to 2 divided by n plus 1 to the power of n divided by n minus 1. This derivation we have obtained, or we can write this as Pt divided by P1 is equal to 0.58 for dry saturated steam. So yesterday we were in previous problem we were using superheated steam, that's why this ratio was 0.546. Now here we are using dry saturated steam, therefore this ratio is 0.58. So this n value we have to substitute as 1. N is equal to 1.13. So if we substitute n is equal to 1.13 in this equation, we get Pt divided by P1 as 0.58. Then from this we can find out entropy at inlet, and that we can equate to entropy at throat. So SF1 is plus of SFG1 is equal to SFT at throat into XT plus plus XT into SFG at throat. So from this we can find out dryness fraction at throat. But when we find out dryness fraction at throat, we can find out enthalpy at throat. And once we know dryness fraction at throat, we can find out specific volume at throat. So once we know specific volume, enthalpy, we can find out velocity at throat, and then we can find out total area. So once we know total area divided by area of area at throat for each nozzle is already given. We can find out nozzle, number of nozzles. Then velocity at exit is required. So to find out velocity at exit, so we can use this equation. So nozzle efficiency is given. So in first case, assuming, what is assumption? Assuming no friction between inlet to throat. So this is assumption. If we are assuming that there is no friction between inlet to throat, then this will be formula. If we consider that there is also friction, then we have to multiply it by nozzle efficiency. So now here velocity at throat can be obtained. H1 is known and nozzle efficiency is known. We have to find out H2. So to find out H2, we must know dryness fraction at 0.2. So here if we see here, steam is going to be wet. Here X2 is the dryness fraction. So X2, to find out X2 dryness fraction, we have to find out this entropy at 1 is equated to entropy at 2. So SF2 SFG2. Then H2 can be obtained. Once we know dryness fraction at 0.2, we can find out enthalpy at 0.2. From this H2, once we know, we can find out V2. Once we know V2 and specific volume small v2, using this formula V2 is equal to X2 into Vg at 2, then we can find out velocity at 2. So number of nozzles is equal to total area divided by area at throat for each nozzle. So now here we have to work out first pressure P1 at pressure throat PT and P2. So we know P1, we know P2, we don't know PT. So PT has to be calculated. So PT divided by P1 is equal to 0.58 for dry saturated steam. So 0.58 means PT is equal to 0.58 into P1. So P1 value we know, 0.58 into P1 is 11 bar. So multiplying this we get 6.38 bar. So now we know pressure at throat. So data can be collected for various pressures. Pressure P1, then pressure PT and pressure P2. So 11 bar, 6.38 bar and 1.5 bar. So this is the information which is taken from steam table. Temperature, specific volume, enthalpy of liquid, latent heat of vaporization, entropy of liquid and entropy of vaporization. So this data is taken from steam table. You know how to collect this data. Now we will proceed to find out the things. First we can find out enthalpy at inlet. So enthalpy of steam at inlet is given by H1 is equal to HF1 plus of X1 HFG1. So actually X1 is not required because dryness fraction X1 is given as 1, that is dry saturated steam. So this is taken at pressure P1 is equal to 11 bar from steam table. So this information H1 is already given us 781.1 plus of X1 value, it is dry saturated steam, means 1 into HFG1. HFG1 is 1998.6. 1998.6. So on calculation we get this enthalpy H1 is equal to 2779.7. 0.7 kilojoules per kg. So entropy of steam at inlet, we can find out entropy of steam at inlet. Condition of steam at inlet is dry saturated steam. This was H1. Now S1 is equal to SF1 plus of X1 SFG1 at pressure P1 is equal to 11 bar. So this data has to be taken from steam table at 11 bar. SF1 is 2.179. 2.179. 2.179 plus of x1 value, it is dry saturated steam, dryness fraction is 1. SFG1 at 11 bar, SFG1 is 4.371. 4.371. So this works out. Entropy of steam at inlet works out to be, let us see, 2.179 plus of 4.371 is 6.55 kilojoules per kg. This is entropy at inlet. Now once we know entropy at inlet, we can try to find out entropy at throat. So to know entropy at throat or enthalpy at throat, HT, we must know dryness fraction at throat. So to find out dryness fraction at throat, the process is isentropic process. Therefore entropy at inlet S1 is equal to entropy at throat. So entropy at inlet is known, which is 6.55. So the formula to find out entropy at throat is SFT plus of X suffix T into SFG suffix T. So this is taken at pressure P. P is equal to 6.38 bar. So this pressure at throat is 6.38 bar that we have calculated. So now the left hand side of this equation is at pressure of 11 bar and right hand side is at pressure 6.38 bar. So left hand side we know that is 6.55, which is equal to SFT. SFT is 1.956. So at 6.38 bar, entropy SF at throat is 1.956. 1.956 plus of X suffix T into 4.780. SFGT at 6.38 bar is 4.780. 4.780. So here on calculation, dryness fraction xt we get as 0.96. Once we know dryness fraction at throat, then we can find out enthalpy at throat. So enthalpy at throat, H suffix T, is given by HFT plus of XT into HFG of T. So HFT, this is taken at pressure PT is equal to 6.38 bar. So HFT at 6.38 bar is 681.5. 681.5 plus of dryness fraction xt, just we calculated as 0.96. 0.96 into HFGT at throat. HFGT at throat is 2076. At throat pressure 6.8, HFGT is 2076.7. 2076.7. On calculation we get enthalpy at throat as 2674.732 kilojoules per kg. So this is enthalpy at throat. One more thing we need, so specific volume at throat, V suffix T is equal to X suffix T into Vg at throat. So xt dryness fraction is known, that is 0.96, just now we calculated, into Vgt. So specific volume at throat at pressure of 6.38 bar is given here as 0.2968, 0.2968, 0.2968. So on calculation we get specific volume at throat as 0.2849, 0.2849 meter cube per kg. We know specific volume Vt, we know Ht, so we can find out velocity at throat. Velocity at throat is given by square root of 2 into h1 minus of ht into 10 to the power of 3. So square root of 2 into h1 value, enthalpy at inlet, which we have calculated as 2779.7, 2779.7 minus enthalpy at throat is calculated as 2674.7 into 10 to the power of 3. So this works out to be, velocity at throat works out to be 458 meters per second. So velocity at throat is known, specific volume is known, mass flow rate is known. So we can find out total area at throat. So total area at throat, total area at throat AT is equal to m into Vt divided by Vt. So this is the equation. Actual equation is m is equal to AT Vt divided by small vt. So this is the problem of multiple nozzles. So m into small vt divided by capital Vt gives us total area at throat. Mass flow rate is known, which is given in the problem. Mass flow rate of steam is given as 4 kg per second. So mass flow rate of steam is given in the problem as 4 kg per second. So here we can substitute 4 into velocity specific volume at throat, which we have calculated as 0.2849. This is specific volume, small vt, 0.2849, 0.2849 divided by velocity of steam is 458 meters per second, 458 meters per second, and on calculation we get total area at throat as 2.4 into 10 to the power of minus 3, or this can be written as 24.88. So this is 88, 24.88 into 10 to the power of minus 4 meter square. So this is also in meter square. So directly we can write this as 24.88 centimeter square. So this is total area or gross area at throat is 24.88 centimeter square. So here number of nozzles used, n, that is nothing but total area or gross area, total area at throat AT divided by cross sectional area at throat of each nozzle assuming all nozzles are of same size, 24.88 centimeter square. So area, total area is 24.88 centimeter square, and area of cross section of each nozzle which is given in the problem is 2 centimeter squares. So this is in centimeter, so we can substitute here 2 centimeters. So on calculation we get number of nozzles as 12.44. so this 0.44 is less than 0.5, so we can say this as 12 or 13 nozzles, approximately 13 nozzles. We cannot use 12 nozzles, 12 nozzles, which will be less, therefore we can use number of nozzles as 13. So if we use the actual method, then this will be 12 numbers, but 0.44 is not too small, therefore we can write it as 13 nozzles, 13 or 12 nozzles. Then we have to find out velocity at exit. So velocity at exit can be obtained. So to know velocity, area at exit, A2 can be obtained by m into v2 divided by v2. So that's why here we need to find out specific volume at exit and velocity at exit. So to know specific volume at exit, we must know dryness fraction of steam at exit x2, as well as to find out this v2 we have to obtain x2. Therefore first of all we will obtain x2. So equating entropy at inlet is equal to entropy at point 2. So entropy at inlet is known, that is 6.55, which we have calculated, 6.55 kilojoules per kg. Now is equal to entropy at point 2 can be written as SF2 plus of x2 into SFG2. So here this is at pressure of P2 is equal to pressure is 1.5 bar. P2 pressure is 1.5 bar. So here this is taken at 1.5 bar. So now 6.55 is equal to SF2 at 1.55 bar. SF2 at 1.55 bar. So 1.5 bar at this pressure, SF2 is 1.433 plus of x2 into SFG2 at 1.5 bar. SFG2 at 1.5 bar is 5.790. 5.790. So from this we can find out dryness fraction at exit as 0.88. So now we know dryness fraction, we can find out specific volume at exit, that is small v2 is equal to x2 into vg at 0.2. so x2 we know 0.88 into vg2 at pressure of 1.5 bar is given in the steam table, which is 1.590. Specific volume is 1.590. Just a minute, let me check. And expansion, okay, that's correct. So now this is 1.590. So specific volume we get as 1.3992 meter cube per kg of V2. So now we know mass flow rate, we know specific volume, we must know this velocity. So to find out velocity we must calculate enthalpy at point 2. So enthalpy at point 2 or h1 minus h2 we can find out. So h1 minus h2 can be obtained or h2 can be obtained. So to know h2 we know x2. So here hf2 plus of x2 into hfg2 gives us enthalpy at point 2. So hf2 from steam table, enthalpy at exit. So here hf2 is given in the steam table as 467.1 plus of x2 value. The dryness fraction is 0.88. So here we can substitute 0.88 into hfg2 at pressure 1.5. This is 6.3. So on calculation we get enthalpy as h2 is equal to 26.24 kilojoules per kg. So this is nothing but enthalpy. So now once we know enthalpy, we can find out velocity of steam at exit. So velocity of steam at exit, V2, velocity of steam at exit, V2 is equal to square root of square root of 2 into h1 minus h2 into nozzle efficiency into 10 to the power of 3. So now we know h1 that we have calculated as 2 into h1 value which we have calculated as 2779.7 2779.7 minus of h2 we have calculated just now. This is 2424 into nozzle efficiency is 88%, means 0.88 into 10 to the power of 3. So on calculation we get velocity at exit as 788.72 meters per second. So exit velocity is known. Now we can find out area at exit. A2 is equal to m into specific volume at exit divided by velocity at exit. So mass flow rate is 4 kg per second, which is given in the problem. 4 into specific volume V2, which is 1.3992 divided by velocity is given as 788.72 at exit. So area which we calculate is 7.09 into 10 to the power of minus 3 meters square, or this can be written as 70.96 centimeters square. So area at exit. So this area which we are going to obtain is the gross area, total area of all the nozzles. So this we can call as a gross area. So area of each nozzle, area of each nozzle at exit is nothing but gross area A2 divided by number of nozzles n. So gross area is 70.96. So number of nozzles we calculated as 13. So divide 70.96 by 13. 70.96 70.96 divided by actual number of nozzles was 12.44, I think 12.44. So we can write here instead of 13 12.44. So we get divided by 12.44, we get 5.7 centimeter square is the area at exit for each nozzle. So individual area of each nozzle is 5.7 centimeter square at exit, whereas gross area of all the nozzles is 70.96. So both answers we have written, thinking that they are asking us to find out individual area or total area. There is confusion in this problem itself, whether he is asking us to find out net area of all nozzles at exit or area of individual nozzle at the exit. So therefore we have obtained both. So now we can write answers. What are the answers? What he is asking us to find out first is number of nozzles, area at throat and area at exit. N, or number of nozzles. We write this as 12.44 and then we approximate it as 30. Then area at throat. So this we are writing as a gross area because individual area is given, so gross area at throat. Gross area at throat is 24.88 centimeter square. 24.88 centimeter square. 24.88 centimeter square. Then gross area at exit A2 at exit, which is given as 70.96 centimeter square. So individual area small a2 we write at exit, which is equal to 5.7 centimeter square. So which area he is asking, whether individual area at exit or gross area at exit, both we have obtained. So this is how we have summarized the answers. So with this I can conclude that the chapter flow of steam through nozzles is covered. Now in next class we will start with the next new unit. Thank you.